sampling distribution and point estimation of parameters. This resolves the course outcome, applies statistical methods in the analysis of data. The intended learning outcomes would be at the end of the lesson, the students are expected to explain the general concepts of estimating the parameters of a population or a probability distribution. Explain the important role of normal distribution as a sampling distribution, and understand the central limit theorem. Point estimator. A point estimate of some population parameter theta is a single numerical value theta hat of a statistic capital theta hat. The statistic theta hat is called the point estimator. Estimation problems occur frequently in engineering. There are different parameters that we want to estimate to find its actual value. We have the mean, the variance, or the standard deviation, the proportion, the difference in means, the difference in two population proportions. So if we want to estimate the population mean mu, the best estimator or the best point estimate that we can use is the sample mean. So for mu hat, we use x bar. For the variance or the standard deviation, sigma squared or sigma, we use the point estimate s squared. So it's counterpart, it's sample counterpart. Um, if you want to estimate sigma or sigma squared, you use its counterpart s or s squared. For the proportion, to estimate the population proportion P, we use the sample proportion x over n. So we divide the number of success x divided by the total possible outcomes n. And to estimate the difference of two means, mu1 minus mu2, we use the difference of two sample means, x1 bar minus x2 bar. And the difference of two proportions, p1 hat minus p2 hat, is equal to the difference of their corresponding samples, x1 over n1 minus x2 over n2. Sampling distribution. The sampling distribution of a sample statistic is the distribution of values for a sample statistic obtained from repeated samples, all of the sample size and all drawn from the same population. So we are considering a repetitive sampling procedure. We're going to obtain a sample from a group of population and we're going to try it several times and prove that it is not by chance alone. So the sampling distribution of a sample mean is a theoretical probability distribution of sample means that would be obtained by drawing from the population all possible samples of the same size. So let us consider a random sample of x1, x2, and x3 up to x sub n are random samples of size n. So if you have a population of 2 million and then you're going to get equal sample. So say for example, a sample of 100. So you're going to get several samples, 100 each, are independent random variables. So you take randomization. And every X or every sample has the same probability distribution. So that is the sampling distribution. A statistic is a function of the observations in the random sample. So it would be taken from a population. So the observation from the sample would be considered as a statistic. And the probability distribution of a statistic is called the sampling distribution. For example, if you're going to consider the statistic X bar, that would be the sampling distribution of the mean. So this is bounded, or this is guarded by a certain theorem, the central limit theorem. So consider the determining the sampling distribution of the sample mean X bar. The sample mean is, how do we consider, or how do we compute sample mean? It would just be the sum of all the possible values of X divided by the number of data in the sample. So that would be X1 plus X2 plus X3 and so on, divided by N. So we add divided by the number of data. If it follows a normal distribution, the sampling distribution of the mean would be the true population mean equal to mu over n plus mu over n plus mu over n and so on and so forth. So that would be mu, the sum of all the mu's all over n. So it is just simply n. Mu. And the variance would be sigma squared of X bar equal to sigma squared plus sigma squared plus sigma squared and so on all over n. So that would be sigma squared over n. So if we are sampling from a population that has an unknown probability distribution, the sampling distribution of the mean will still be applicable, or will be approximately normal, with the mean mu and variance sigma squared over n if the sample size n is large. So it would approach a normal distribution if we take n to be significantly large. So how do we determine? Various references states that if n would be taken greater than or equal to 40, like Montgomery and Runger, it would be considered large. While if it is generally greater than or equal to 30, we consider it large, from Walpole and other authors. So majority of the authors takes into consideration 30. That is why if you're going to take samples from your data, it is significant that you choose number of samples high enough to satisfy this requirement. So basically, you choose 100 samples and above, just to show that the sample taken is large enough. If x1, x2, up to x sub n is a random variable of size n taken from a population either finite or infinite, with mean mu and variance sigma squared, and if x bar is the sample mean, the limiting form of the distribution of the standardizing formula z is equal to, now it comes from x minus mu over sigma. So it would now be x would be x bar, mu is still mu, and then sigma is now sigma over square root of n. So this is being used, or when n is significantly large, it becomes a standard normal distribution. Now, I want you to observe the case of a die. If you're going to roll a die, the probability for each outcome in a die is 1 over 6. So 1 over 6, 1 over 6, 1 over 6, 1 over 6, and so on. So if you're going to consider that, it would be equal, uniform distribution. So rolling a die would be 1 over 6, 1 over 6, 1 over 6, 1 over 6, and so on. So equal probability or equal chances. However, if you're going to roll a die twice, the outcome of having an average of 1, so that means 1, 1, is the slimmest chance. This is somewhat similar to an outcome of an average of 6. So that is 6.6. So that is also very, very slim. So this has the lowest probability. There are only two possible outcomes that would give an average of 1, which is 1, 1. And there is only one outcome that would give us an average of 6. So that is 6, 6. So for this one, it would be 1.5. So that would be for the case of 1, 2, and 2, 1. For 5.5, it would be 5, 6, and 6, 5. For for 3.5, it would be quite plenty. So it would be 3, 4, 4, 3, um, 2, 5, 5, 2, 1, 6, and 6, 1. So there would be a plenty number of outcomes that would have an outcome of 3.5. Now, that is for 2 dice. If you're going to have 3 dice, so the tails decreases its chances, but the center approaches a smoother curve. And if you're going to roll 10 die, and so on. So as what you can see, a non-normal distribution approaches a somewhat normal distribution. A non-normal distribution approaches a standardized normal distribution if we have several trials or several attempts. Let us have this example. Resistors. An electronics company manufactures resistors that have a mean resistance of 100 ohms and a standard deviation of 10 ohms. What does this problem tell us? That the mean is 100 and the standard deviation is 10. The distribution of resistance is normal. Find the probability that a random sample of n is equal to 25 resistors will have an average resistance of fewer than 95 ohms. So we're looking for the probability that the sample distribution of the mean would be having a probability of lower than 95. So let's have that with this illustration. So the mean is at the center, it would be 100. So this is the mean. Now the standard deviation is 2. How come it becomes 2? So the sampling distribution, the mean of the sampling distribution is sigma over square root of n. So that would be equal to 10 over square root of 25 because n is given as 25. So sigma is 10 over 5, which is 2. That is why the sampling distribution of the mean is 2. Now, if we're looking for the probability that x bar is less than 95, it would be the probability that z is less than 95 minus the mean, 100 over 2. So that is the probability of 95 minus 10 is negative 5 over 2. So that's negative 2.5. And we look at the probability to the left of negative 2.5. So we can use your calculator or you can use other techniques to solve for the value. So that would be, I think, negative 2.5 would be um, 0.00621. Let's have another problem. Suppose that a random variable x has a continuous uniform distribution with f of x is equal to 1 half for x is from 4 to 6 and 0 otherwise. Find the distribution of the sample mean of the random sample of size n is equal to 40. So first, I think it's better to identify the mean, which is just a plus b over 2. So a is 4, b is 6. So 4 plus 6 is 10 over 2. So the mean is 5. While for the variance, it would be b minus a squared over 12. So that is 6 minus 4, which is 2 squared, or 4 over 12. So that is 1/3. So to visualize that problem, we have this one. It is a uniform distribution with a mean 5. The distribution is uniform from 4 to 5, uniform. And the variance is, so this is the variance of x bar. So the mean of x bar is equal to the mean, which is 5, and the variance of x bar is 1 over 3 divided by n, which is 40. That's why it is 1 over 120. So that's the distribution of the sample mean.